Hello everyone. This week we will cover Module 4 of Chem 1. We will discuss Lewis dot structures and the Lewis bond theory. By this time, you should already be familiar with the three important learnings from the previous modules. First, chemical bonds form between valence electrons of two or more atoms based on the octet rule. 2. The position of an element in the periodic table tells us how many valence electrons it has. And 3. Electron configurations allow us to identify the orbitals holding valence electrons. In our previous lecture, we represented the sharing of valence electrons between atoms as orbitals sharing their valence shell. There is an easier and well-established method to show how atoms share their valence electrons to form chemical bonds. This method is called the Lewis dot structure. Gilbert N. Lewis was a British scientist who invented a method to illustrate how covalent compounds combine their valence electrons to form chemical bonds. Lewis created this method primarily to demonstrate a bonding theory that he was proposing. In 1916, Gilbert and Lewis proposed that atoms combine in order to achieve a more stable electron configuration of 8 valence electrons. Valence electrons play an essential role in chemical bonding, and an electron pair that is shared between two atoms constitutes a covalent bond. Lewis dot structures or Lewis structures uses dots to represent valence electrons. It uses the periodic table of elements to determine the number of dots. It applies to covalent bonds and elements in the first period of the periodic table, and it can also be used to represent ionic compounds and polyatomic ions. We can represent the valence electrons of atoms by drawing dots around the element's name. In this example, we have taken representative elements from certain groups of the periodic table. We learned in Module 3 that an element's group number tells us how many valence electrons it has. For instance, Group 1 elements like sodium have 1 valence electron. Group 2 elements like magnesium have 2 valence electrons. Groups 3 to 12 elements have varying numbers of valence electrons. Group 13 elements like aluminum have 3 valence electrons, and so on until group 18 elements like argon, which have 8 valence electrons. Let's illustrate the Lewis dot structure first with diatomic molecules. Hydrogen has 1 valence electron, so we can draw 1 dot on either side of hydrogen to represent this electron. We learned in the previous module that electrons are more stable if they are paired, so two atoms of hydrogen can pair their respective electrons to form hydrogen gas. For most other atoms, the octet rule governs the pairing up of valence electrons. In this example, bromine has 7 valence electrons. Each bromine atom needs only 1 more electron to fulfill its octet requirement. Thus, two bromine atoms can form a bond with each other to form a diatomic molecule. Beyond diatomic molecules, the octet rule still governs how to draw Lewis dot structures. The rules are pretty simple. First, we determine the number of valence electrons of each atom. We write their individual Lewis dot structures. Let's use carbon tetrafluoride and water as our examples. We can draw each atom in these two molecules with their valence electrons as dots, then count the total number of valence electrons for all atoms in the molecule. Carbon tetrafluoride has a total of 32 valence electrons, and water has a total of 8 valence electrons. Next, we arrange the atoms in a basic outline. In general, the least electronegative element goes first or in the middle. Hydrogen is almost always on the outside. For carbon tetrafluoride, we know that carbon is the central atom because it is less electronegative than fluorine. The fluorine atoms are terminal atoms that can pair with each of carbon's 4 valence electrons. For the water molecule, oxygen needs 2 electrons to complete its octet. Thus, we can position each of the hydrogen atoms on either side of oxygen. Finally, we connect the atoms. Hydrogen only needs 2 electrons and the other atoms should have 8. We then count the total number of valence electrons again to make sure that we have included all the dots in the structure. The octet rule is thus satisfied for carbon, oxygen, and fluorine. Note that in a Lewis structure, we call electron pairs that do not participate in the bonding as lone pairs, and electrons that participate in the bonding as bonding pairs. Finally, we can replace the paired electrons between the two atoms with a line to represent single bonds. Then we fill in the terminal atoms with the lone pair electrons to show that they fulfill the octet rule. We also include lone pairs in the central atoms, as in the case of oxygen in the water molecule. Not all molecules share electrons using single covalent bonds. In fact, many molecules have atoms that share more than one electron with another atom. Carbon dioxide is the most important compound needed by plants for photosynthesis. Carbon has 4 valence electrons and oxygen has 6. If carbon dioxide was made up of single bonds only, there would be an imbalance of valence electrons, with one oxygen atom having 3 lone pairs, whereas the other has only 1. The carbon atom would have 2 lone pairs. To achieve more stability, carbon forms a double bond with each of the oxygen atoms. Doing so results in a balance of unpaired electrons on both oxygen atoms. Other molecules share not just single or double bonds but also triple bonds. The nitrogen diatomic molecule N2 is a gas that makes up 70% of our atmosphere. Nitrogen has 5 valence electrons. N2 forms from the pairing of 3 of these valence electrons to form a triple bond. Hydrogen cyanide is a molecule that has both a single bond and a triple bond. One hydrogen atom pairs with one of carbon's 4 valence electrons, and the remaining 3 valence electrons of carbon pair with 3 of nitrogen's valence electrons in a triple bond. Many of the organic compounds that we will study in Unit 2 have double bonds and triple bonds. For instance, ethylene has one double bond between the 2 carbon atoms. Acetylene has a triple bond between the 2 carbon atoms. Drawing the Lewis dot structures for ionic compounds is not the same as that for covalent compounds, but the concept of fulfilling the octet rule remains the same. Remember that in ionic compounds, the cation loses its valence electron to the anion. Let's use potassium iodide, calcium chloride, and iron 3 oxide as examples. In potassium iodide, potassium loses an electron to iodine to form the potassium ion and the iodide ion. To show the loss and gain of electrons, we place the cation and the anion separately in brackets, indicating the charge in the superscript. In calcium chloride, calcium loses 2 electrons to 2 atoms of chlorine to form the calcium ion and 2 atoms of the chloride ion. For iron 3 oxide, 2 atoms of iron and 3 atoms of oxygen are needed. So we can draw 2 atoms of iron with 3 valence electrons and 3 atoms of oxygen, each with 6 valence electrons. For the oxygen atom to fulfill its octet rule, it needs to gain 2 more electrons. So this iron donates 2 electrons to this oxygen. This iron donates 2 electrons to this oxygen, and this oxygen atom can receive 1 electron each from the remaining electrons of the 2 iron atoms. The Lewis dot structure for this compound becomes 2 atoms of iron with a 3 plus charge and 3 atoms of the oxide ion with a 2 minus charge. Remember that when we write the ionic formula, we need to make sure that the total charge of the ionic compound is 0. So in this case, the iron has a charge of 6 and the oxide ion has a charge of minus 6. So the total charge is 0. Drawing the Lewis dot structures of polyatomic ions works in the same manner as those for covalent compounds. Let's use the ammonium ion and the sulfate ion as our examples. First, we determine the total number of valence electrons for all the atoms. Then we create a skeleton of the possible bonding pattern. We then pair up the valence electrons. Note that the ammonium ion has a +1 charge. This means that this ion loses 1 electron. Nitrogen has 5 valence electrons, but there are only 4 hydrogen atoms. Each hydrogen atom can pair up with 4 of nitrogen's valence electron. The remaining valence electron is given up to form the ammonium ion. In the case of the sulfate ion, sulfur and oxygen both have 6 valence electrons. Each oxygen atom needs 2 more electrons to fulfill its octet, so a total of 8 electrons would be needed for all 4 oxygen atoms. But sulfur only has 6 valence electrons. However, the sulfate ion has a -2 charge. This means it has 2 additional electrons that can be used to pair up with all 4 oxygen atoms. We can then create the possible bonding pattern by putting sulfur as the central atom, since it has a lower electronegativity than oxygen. We can place the 4 oxygen atoms around sulfur. We can then connect the oxygen to the sulfur using single bonds, and then complete the structure by filling in with the unpaired electrons of oxygen. Now, this structure looks correct because all the atoms fulfill the octet requirement. However, the actual structure for the sulfate ion that is observed in laboratory experiments is different. The actual structure has the sulfur atom double bonded to 2 of the oxygen atoms, like so. We then complete the Lewis dot structure by filling in the oxygen with unpaired electrons, and then put them in brackets and indicate the 2 electrons that were gained to form the sulfate ion. The reason for this other structure is what's called a formal charge. We will discuss formal charges as the next topic. Recall that in Module 3, we learned that some atoms do not always follow the octet rule. Sulfur is one of those exceptions. It can share 2 valence electrons to achieve the octet, or it can share each of its 6 valence electrons to 6 other atoms. In the case of the sulfate ion, Sulfur shares each of its 6 valence electrons with 3 oxygen atoms, plus an additional 2 electrons for the 4th oxygen atom. Let's move on to the next topic on formal charges. The formal charge is the charge calculated for an atom in a Lewis structure on the basis of an equal sharing of bonded electron pairs. The formal charge helps in choosing the best Lewis structure for a compound with several possible Lewis structures. The formal charge can have 3 possible values, -1, 0, or +1. The formal charge can be computed given the following formula. Formal charge equals valence electron minus lone pair electron minus bonding electron divided by 2. The formal charges will tell us whether the structure we have drawn is possible or not. If the formal charge is 0, then this structure is possible in nature. If the formal charge is -1 or +1, this is also possible in nature. If the formal charge is -2 or +2, then this is impossible in nature. Let's have nitric acid as our example. We compute the formal charge for each of the atoms in the molecule. A neutral hydrogen atom has 1 electron. Hydrogen has no lone pairs of electrons. Hydrogen shares 2 electrons with oxygen. Based on the formula, the formal charge of hydrogen is 0. Then we go to the first oxygen atom. Oxygen has 6 valence electrons. It has 4 bonded electrons and 4 lone pair electrons. Based on the formula, the formal charge of oxygen is 0. Then we go to the next oxygen atom. It has 4 bonded electrons and 4 lone pair electrons. Based on the formula, the formal charge of this oxygen is 0. The last oxygen atom has 2 bonded electrons and 6 lone pair electrons. Based on the formula, the formal charge of this oxygen atom is -1. Finally, we compute the formal charge of nitrogen. Nitrogen has 5 valence electrons. It has 8 bonded electrons and 0 lone pair electrons. Based on the formula, the formal charge of nitrogen is +1. A Lewis structure is not complete unless formal charges, if any, are shown. We enclose the molecule in brackets, then write the formal charge as a superscript. Let's go back to the Lewis structure of the sulfate ion that we did earlier. The reason why the sulfate ion has a different Lewis structure than what is theoretically possible has to do with having the correct balance of formal charges. In the theoretical structure, each of the oxygen atoms is bonded to the sulfur atom using single bonds. If we calculated the formal charges of all the atoms in this ion, the oxygen would all have a -1 formal charge. The sulfur would have a formal charge of +2. Now we mentioned earlier that a +2 formal charge is not possible in nature, so this original structure of the sulfate ion cannot exist. The most plausible structure for the sulfate ion is one where the sulfur atom is double bonded to 2 of the oxygen atoms. If we calculated the formal charges of all the atoms here, the double bonded oxygen atom would now have a formal charge of 0. The single bonded oxygen atoms would still have a formal charge of -1. the sulfur atom would now have a formal charge of 0. So with this structure, there is a balance of formal charges. The other two oxygen atoms still has a formal charge of -1, but this is okay because the sulfate ion has a 2- charge. If we were to draw the Lewis dot structure for the thiocyanate ion, we might come up with any of three possible structures. In all three cases, the octet rule is fulfilled and the formal charge is the same, that is -1. In certain cases, molecules can have the same elements, but it can be arranged differently by the Lewis bonding theory. The different Lewis structures are called resonance structures. Many polyatomic ions have resonance structures. For example, the carbonate ion has 3 resonance structures, with the C double bond O having 3 possible locations. The sulfate ion, whose Lewis dot structure we did earlier, has no less than 6 resonance structures, with the 2 S double bond O's having 6 possible locations. And that ends our lecture on Lewis dot structures and the Lewis bond theory. The deadline for submission of Module 4 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.